Okay, in this segment we're going to look at how to read off the logic function implemented by a particular logic gate. So let's suppose we have an example of a logic gate here. Let's just do something like I'm just making this up. Off the top of my head here, so let's say this is A, B, C, and D. This is our output Y. And then we would have, for the pull-up, something like this. Where we have A, and we have B, and then C and D. Something like that. Okay. So we'd like to know what logic function does this gate implement. Well, there's a couple of different ways we could get at this. One would be to focus on the conduction conditions for the pull-down network. That's usually what I go for. So I know that the conduction condition for the pull-down network here, I can read directly off the network because I have A in series with B and parallel with C in series with D. And I can interpret series as conjunction or and I can interpret parallel as disjunction or. And so the conduction condition for the pull-down network would be Y bar. So Y bar from PDN, conduction condition, we have that Y bar is equal to A and B or CD. Okay, so we have A. The A transistor is in series with this other piece of the network in parallel. And so we put that conjunct in parentheses, and that in turn is a parallel, which is a disjunction. And the two disjuncts here are B, or we have a third piece here, which is C in series with D. So that's C and D. And so from that, we have that Y, by just complementing both sides, is basically A NAND B or CD. We could alternatively look at the pull-up network. So from the P conduction conditions, we get directly Y. And so in this case, we have Pmos transistors, and so the Boolean variables that go into the gates are going to have an overbar. Okay, so in this case we have not A or something, and that something is going to be a conjunction, because I don't need to parenthesize it, B in series with not C or not D. And this is another form of this expression, and the two are related to each other through De Morgan's law, and we can apply De Morgan's laws repeatedly to derive that. So if we, for instance, focus on this particular disjunct here, this is equal to not A or, well, we pop the overbar, let's say up out of this one here, B, not B, or CD. Okay, and we can apply De Morgan's law again to this, not A or, well, pop the overbar up one level, B or CD, like so. So you pop the overbar up one level and you change or to and. So this and became or, and these overbars pop up one level. And so one last time, we get A and B or CD bar. So these two forms are just different logically equivalent forms of the same expression, and either one of them will do. I usually focus on the pull-down network and just put an overbar over the whole thing. Your mileage may vary. This also brings me to a somewhat related topic. So we can read the Boolean expression off of the network of transistors, but we can also synthesize the pull-up network directly from the pull-down network, or vice versa. And that's, in fact, I just drew this pull-down network and then in my head synthesized the pull-up network that goes along with this. And the way you do that is you interchange Nmos and Pmos, and you interchange series and parallel. It takes a little bit of practice, but you can do it with a little bit of practice, and it's very, very simple. So suppose we have I don't know, the following pull-up network. We have two transistors in parallel in series with third transistor here. We call these A, B, and C, and then this is the output of our gate Y. Suppose we want to synthesize the pull-down network that goes along with this to make this a fully complementary combinational gate. Okay, so that means that we want the pull-down network to embody Y bar as its conduction condition. And so to do that, we could take this and apply De Morgan's law to the equation. We could take the equation that corresponds to the pull-up network's conduction condition, apply De Morgan's laws to get the complement, and then go from the expression to the network. But we can also just go to the network directly by interchanging series and parallel and interchanging Nmos and Pmos. And that turns out to be exactly equivalent to applying De Morgan's law in the realm of the Boolean expressions. So here we have effectively a piece of the network which is in parallel, and that appears in series with another piece of the network. Okay, so we have two things in series, and so at the upper level we're going to have two branches in parallel in the pull-down network. One of them is going to correspond to the C transistor here, okay, and that's going to be a C transistor, and that appears in parallel with the other piece of the network that corresponds to the A and B part. So the C part was in series with the A and B part, so the C part here is going to be in parallel with the A and B part here. And so the A and B part, in turn, this is in parallel, so the A and the B part is going to comprise two transistors in series in the pull-down network. something like that. Okay, and again, it's very easy to get the conduction condition for the pull-down network. So your y bar would be equal to C or AB, which implies that y is equal to C nor AB, like that. Okay, so I hope you get the idea of how to do this. It takes a little bit of practice, and you can make up some examples for yourself if you care to. I want to move on now and talk about the voltage transfer characteristic of the inverter and several important properties that it has. So we're going to look at the Cmos inverter. Voltage transfer curve, which means that we're thinking about now the voltage as an analog quantity that goes from 0 to VDD, and the output voltage in the same way. And we want to plot a V out versus V in. Okay, so we're going to construct this. So Cmos inverter VTC. We're going to try to construct this from what we know about how transistors work. Okay? So the first thing we're going to do is say, let's call this I sub P and I sub N. And V out, for a given value of V in, V out will be whatever voltage is necessary at the common drain node of the two output transistors to make Kirchhoff's current law satisfied. Okay? So first of all, let's think about what the two transistors' saturation current looks like as a function of V in. Okay, so this is going to be I sat N or I sat P as a function of V in. Okay, so here's VDD, and here's 0. And what we're doing is we're imagining having the output voltage somewhere where the transistors are saturated, and we're plotting the saturation current as a function of the gate voltage. Okay, and this is going to be on a linear scale. And so on a linear scale, before we get to VTN, VTON, the current's going to look like 0 in the Nmos transistor. And then, once we get past the threshold voltage, it's going to look like a parabola that opens up. Maybe something like that. Okay? And this might be hundreds of microamps, or it might be milliamps when it gets up to the top here. And then for this down here would be the subthreshold region, or the weak inversion region. And this would be the strong inversion region, where we have a square law relationship. And down here is basically all those orders of magnitude of current that are basically too small or indistinguishable from 0 on this scale. Up here we have, let's say, VDD minus VTOP. Okay, so this might be like, let's say, 4.2 volts or something like that if we have a 5 volt power supply. When we're up in this range of voltages, where we're less than a threshold voltage below VDD, which is where the source of our Pmos transistor is, we're in weak inversion with a Pmos, and so its current would be indistinguishable from 0 on this scale. And then as we get to lower and lower gate voltages, we're going to, again, have a parabola which opens upward, something like that. And so this is the Nmos, and this is the Pmos. And so down here for the Pmos, that would correspond to strong inversion. And up here for the Pmos, this would correspond to weak inversion. And this is, like I said, this is the common gate voltage. And from this curve, what we're going to do is we're going to be considering different gate voltages and what the relative saturation current level of the Nmos and the Pmos transistors look like, so that we can plot a set of drain characteristics for the Nmos and the Pmos transistors. Okay, so we're going to take over here. We're going to think about some drain characteristics under different scenarios. Okay, so this is going to be IN and IP, the current now in the Nmos and the Pmos transistor, as a function of their common drain voltage, V out. Okay? So, and we're going to get a whole family of curves for each different gate voltage that we apply. So first of all, let's think about Vn equals 0. So when Vn is equal to 0, the Nmos transistor is down here, and the Pmos transistor is up here. Okay? So that says that the saturation current level for the Pmos transistor is going to be way up here, and the saturation current level for the Nmos transistor is way down here. And so the drain characteristic for the Nmos transistor is just going to be indistinguishable from the current equals 0 axis, the V out axis here. You know, it might be a few picoamps of current or something like that. There would be an ohmic region and a saturation region, but you can't see it on this scale. Whereas for the Pmos transistor, we're way above threshold, and so we have here a drain characteristic that would look something like maybe like this, and then it would look parabolic. And so this would be the ohmic region here, and this would be the saturation region up here. Okay, this part of the curve looks like an upside down parabola opening downward, so you get down to V out equals VDD, and then there's a flat region up here where it saturates here. And the question is, where is the output voltage going to wind up? Well, we said that the output voltage has to adjust itself so that Kirchhoff's current law is satisfied. So the drain characteristic, the voltage at which Kirchhoff's current law is satisfied, will be the one where IN is equal to I sub P. So where these two drain characteristics intersect is where the output voltage will be. Right? So we have here the Nmos drain characteristic and the Pmos drain characteristic. They correspond to their current, their saturation current levels. Well, where do they intersect? Well, they intersect up here, where the Pmos transistor is deep in the ohmic region with almost no voltage across it, just enough voltage across it to pass the tiny amount of current that's being sunk by the Nmos transistor. Okay? So we have one point on the voltage transfer curve, which is V out versus V in. And so let's say this is VDD and this is VDD. And this is the identity line here, V out equals V in. And so we considered V in equals 0, and we found that V out is going to be pretty much up near VDD, which is comforting because if we put in a 0, we expect to get a 1. Okay? So let's consider a voltage here that is an input voltage which is maybe on the order of VTON, right? So let's say Vn is about the threshold voltage for the Nmos transistor. Not quite there, but getting there. Well, still on this axis, the saturation current for the Nmos transistor pretty much looks like 0. Okay, but for the Pmos transistor, we've moved down here. Right, so we've turned the Pmos transistor off a little bit, but and then we've turned the Nmos transistor on a little bit, but it still looks pretty much like 0. So the drain characteristic for the Nmos transistor is still going to look pretty much the same, whereas for the Pmos transistor, we've moved down to a slightly lower drain curve here, which might look something like that. Okay, so let's label this here VTON. Well, so here's the new Pmos drain characteristic. Question is, where do they intersect? Well, they're still pretty much intersecting at VDD. Maybe it's a little tiny bit lower than VDD, but it's still pretty much at VDD. Right, so you kind of get the sense that the curve here is going to be pretty close to VDD for a while. Right, because all of these drain characteristics in this whole range of gate voltages are going to be very, very indistinguishable from 0 on this linear scale. All right, so that's what's going on up here at the relatively low gate voltages. Let's think about maybe what happens a little bit above threshold. Let's say, well, I don't know, right here. Okay, well now we're starting to move a little bit on the Nmos side of things, right? So we're moving the Pmos down to a slightly lower. So we're maybe right here somewhere. We're moving the Pmos down to a lower drain characteristic. Maybe something like this. Which would correspond to this point. But now our Nmos drain characteristic is looking something like that. Okay, so now this is the Nmos, and this is the Pmos. Well, the intersection point is still up pretty close to VDD here. Okay, that the Pmos transistor is still in the ohmic region on this scale, and so maybe we're down here somewhere. Okay, so let's look at this point. This point here is interesting because at this particular point we have the saturation currents being pretty much equal to each other, right? So the Nmos current, or the Pmos current characteristic is going to look something like that, and the Nmos one is going to look something like that, and maybe they will intersect somewhere here. Okay, the flatter these curves are, the steeper this characteristic will be. It's going to be something like that. Or actually, I guess we're a little higher here, so maybe we're more like here. Okay, Let's go a little higher. So still below the threshold for the Pmos. And maybe if this is VDD minus VT P VTOP, maybe we're somewhere in this neighborhood here. Well, in that case, so I think this is third point here. The fourth point is going to be slightly below the threshold for the Pmos transistor, so that they're still both in strong inversion here. Now the Pmos drain characteristic is going to be getting pretty close to the axis, but not exactly there. The Nmos characteristic, however, is coming up. So the Nmos characteristic, the saturation current, might look something like that. Okay, so where are they going to cross? Well, they're going to cross down here, pretty close to ground. This is the Nmos. So down here, we're talking about something like that. And then if we get into the range of in weak inversion for the Pmos, and of course we're going to be on the axis for the Pmos. And again, there is still an ohmic region and a saturation region. The ohmic region will be way up here near the VDD. The saturation region would still be here over most of the range. But now it's not visible on this scale. And so for the Nmos transistor, we're moving up to a higher drain curve, which might look something like that. And the intersection is going to be way down here somewhere, very close to V out equals 0. And of course, if we go full up to VDD on the input, we haven't really moved the Pmos drain curve. The Nmos drain curve will move up to its highest level, and maybe it'll look something like that. The intersection is going to be really, really close to 0. And so that's Vn equals VDD. Okay, so we're getting here the saturation current level from the gate voltages, which gives us a pair of drain characteristics. And where those drain characteristics intersect here, that tells us the output voltage, or the common drain voltage, where the circuit will operate. And so we have this type of curve. It's an S-shaped curve, and it's flat here and flat here, and it's steep here in the middle with a negative slope. Okay, and there are some very, very important features of this curve here, and some particular voltages that are defined on this curve. One of them is called the transition threshold, which is typically denoted V sub m. And the transition threshold is basically where the input voltage and the output voltage are equal to each other. So it's where this CMOS inverter VTC crosses the identity line. That's where V out equals V in. Two other very important points on this curve are defined to be where the slope of the tangent line is equal to -1. Okay, where the slope of the tangent line is equal to -1, I'm going to erase these here. So this particular point is called VIL, and this one down here is called VIH, and the output voltage that corresponds to this one here would be called VOH and VOL. Okay, and what these points define are the ranges of input voltage which are considered 0 and 1, and the range of output voltages which are considered 0 and 1. So the range of voltages between 0 and VIL is an input 0. And the range of voltages between VIH and VDD is a legitimate 1. And the same is true here. This is an output 0, and this is an output 1. Now, why does the slope of this line here being equal to -1 make sense for a line of demarcation? Well, really quickly, the idea here is that the slope of the tangent line to this VTC is the incremental gain of the circuit. So if I wiggle the input voltage around in a certain range, the slope of the tangent line tells me by how much the output voltage is going to wiggle around. And so in this range of zeros and ones, the slope of the tangent line is less than 1 in magnitude. And what that means is that any wiggling around of the input voltage is going to get compressed. It's going to get attenuated by the slope of by the gain of the Cmos inverter. And so any of this wiggling around will get attenuated. And that's good, because wiggling around on the input voltage of a digital gate would be basically noise. Unwanted signals corrupting the logic signal. And so the fact that the incremental gain of the circuit in this range is less than 1, and substantially less than 1, means that the gate has the ability to suppress noise on its input. And the same is true here. The magnitude of the incremental gain is less than 1. And so in this range of input voltages, what we get is noise suppression. And so we also get that this whole range of input voltages gets compressed into a range of output voltages which is closer to, in many cases, the opposite rail as we were on the input. So we also get something called logic level restoration. So these ranges for 0 and 1 give us logic level restoration and noise suppression. Which are both actually critical for the operation or the reliable operation of digital circuits of any complexity. So the shape of this voltage transfer curve, where it's flat here and flat here near the rails, and has to, by definition, then be steeper in the middle here, is actually quite critical for the reliable operation of digital circuits. So this inverter VTC obviously is not necessarily exactly telling you the story of all digital gates, especially complex ones with multiple inputs, but it is a prototype. You'll find that all Cmos gates have a similar kind of S-shaped voltage transfer characteristic like this, which is flat near the rails and steep in the middle. It's just that when you have more than one input, you obviously have multiple dimensions for the input space, and if you just look at the VTC with respect to one input for different values or different combinations of the other inputs, it'll shift around some depending on what those other inputs are. But it generally will have this kind of shape, and this kind of shape is actually, like I said, quite critical for the reliable operation of digital gates. Okay, that's going to be it for this segment, and we'll see you next time.